All right, we are now on example 5 from the 3.4 notes. So my recommendation is to try these next 3 problems on your own. Pause the video, give them a shot, and then restart the video and see how you did. So if I were doing number 5, there's no way that I would use the product rule for this. I would distribute first. Maybe I would rewrite that 5 times the square root of x, just to help me with the distributive property here. But then I would rewrite this as 25x to the 5 halves minus 20x to the 3 halves. Remember, you are adding those exponents together. And now I'm going to use the product rule. And so then I would end up with, let's see, 25 times 5 would be, oh, this is interesting. I didn't pay attention. We are finding the second derivative. So we're going to need to find the first derivative and then take the derivative of the derivative. Just FYI. All right, let's use the power rule here. I'm going to get 125 over 2 times x to the, I'm going to take 1 away, so 3 halves, minus 30 x to the power of 1 half. I'm not going to stop and factor this. This is not my final answer. I can take care of my factoring and simplifying of this after I've done the second derivative. I'm going to use the power rule again. I will get 375 over 4 times x to the power of 1 half minus 15x to the power of negative 1 half. Now I'm going to need to factor this. Now, if you're having trouble factoring with a fraction, one thing you can do is just write both of these values with a denominator of 4. You might like that better. I don't know. Some people do. 15 is the same as 60 over 4. So if you prefer to do that, it might help you with your factoring. I do need to take out this denominator of 4. That is absolutely required. And then 375 and 60 both have a factor in common of 15. So I'll take that out. And then I need to take out x's to the lowest power, which is to the power of negative 1 half. I've taken out the denominator. 15 times 25 would give me the 375, and 15 times 4 would give me the 60. Let's look at the powers of x. X to the power of negative 1 half would need to be multiplied to x to the power of 1 to get back to this 1 half here. And I took out all of the x's from this one. Just to finish this up, I need to take this power and move it to the denominator. And so that will go on the denominator with the 4. I don't mind if you write that as the square root of x or if you write that as x to the power of 1 half. That is your choice. And both are considered perfectly acceptable. All right, we are going to again work on finding higher powers of derivatives. So we're going to find a second derivative and a third derivative. This is not a situation where you should use quotient rule. Do not use quotient rule here. 8 is just a constant. You're not dividing a variable on the numerator and a variable on the denominator. If you have an opportunity to rewrite these problems so that you would not having used quotient rule, do that. I'm going to rewrite this as negative 8 times x to the power of negative 1 half. And then I can use power rule. Power rule is so much easier than quotient rule, so if you have an opportunity to use that, do so. So f prime of x would then be 4 times x to the negative 3 halves. That's not actually what I'm looking for, but I need to find that before I can find the second derivative, which would be negative 6x to the power of negative 5 halves. And the third derivative, which would be, what was that, 15x to the negative 7 halves. Now both of these need to be a little bit simplified because I can't keep that negative power in the expression. So you could write this like that. You could write this one with a positive power on the denominator like that. You might see these simplified a little bit more just because x to the power of 5 halves really means the square root of x to the 5th, and you can take some powers out from that. I don't care. You can simplify that or not. I mean, you can get really intense with this stuff with like absolute values. We could assume that x is positive or not. I'm not too stressed about that. So you could write this like this. I'm happy with this answer though. But if you see it simplified like that, that's totally fine. Same type of thing here. You could take out, if you've got the square root of x is 7, you could take out 3 pairs of x's. Technically, you would need an absolute value there to make sure that those all stay positive, but you're really not going to need to go down that rabbit hole. You can just leave them like that. All right, number 8. This one's or number 7. This is a really interesting problem because of the fact that we have 2 different rules in this problem. Now, I also need to give you, I think you guys may have done e to the x in the last video. But just in case, if you've never seen e to the x, it's very interesting is that e to the x is its own derivative. So if we have y is equal to e to the x, then y prime is also equal to e to the x. And that's because if you graph e to the x at any point, if you look at the slope of the tangent line, that slope would be the exact same as the height of the function. It's a crazy thing to think about, but nonetheless, it's true. All right, so that is a true statement. If you don't know that yet, you might want to write that down. So the reason this problem is so intense is because on the numerator, we need to recognize that this is product rule, which is really hard for kids to recognize. This is 5x times e to the x. That's product rule because they both of these expressions have an x, or variable, and then the denominator here helps us see that this is quotient rule. So, hold on tight for this one. One thing that you'll want to see is what's the main rule that's happening. The main thing that's happening here is this division. So we're going to start with the quotient rule. And as we're working on this problem and we use the quotient rule, we are going to have to then use the product rule as part of our quotient rule. That gets kind of intense. All right, let's see how it goes. So if we want to find the derivative, let's start with our calculus first, which is really going to only be one step. So to use the quotient rule, we want to take the denominator, and here's where it gets tough. I want to multiply it by the numerator's derivative. Well, as I take the derivative of this numerator, I have to use product rule in order to do that right here. So I'll come back to that, okay? Kind of working on my quotient rule a little bit more. I will subtract from this the derivative, or subtract from this the numerator times the derivative of the denominator. That one's easy, yay. And then divided by the denominator squared, which I'm going to go ahead and never FOIL that out. Okay, I'm going to leave that. All right, so but let's go ahead and do this derivative of the numerator that needed to be placed right here. We're going to use the product rule for this. So I'm going to do the first function times the derivative of the second, e to the x is its own derivative, plus the second function times the derivative of the first. Okay, that's a little intense. Now we have to try to simplify this. Okay, so we're done with the calculus. Calculus, done. Now we do algebra. Lots and lots of different ways to think about how to simplify this. Lots of different ways. I'm going to try to factor this right away. That may not be the way that you want to do this. In fact, maybe I won't this time. Maybe I'll distribute this out a little bit. But you could choose to actually factor it right away and take out a 5 e to the x from all terms. But I'll distribute this because it might be a little easier to see as you're first learning this. So this would be 5x cubed e to the x plus 5x squared e to the x. I'm just distributing here. I'm foiling this out. Minus 25, let's see, x e to the x. And minus 25 e to the x. And then minus 10x squared e to the x. All over the denominator. Okay, checking to see if there's any like terms. There are 2 like terms here that I can combine. Right here and here. So that's kind of nice. I'll go ahead and combine those. I end up with 5x to the third e to the x minus 5x squared e to the x minus 25x e to the x and minus 25 e to the x all over x squared minus 5 quantity squared. So I've expanded this out, combined like terms. I am now going to factor out a greatest common factor. All the terms are divisible by 5. and all the terms have an e to the x. So I'm going to factor out 5e to the x, leaving me with x cubed minus x squared minus 5x minus 5 all over x squared minus 5 quantity squared. Now I did check to see if this factors. It's so close to factoring, but it doesn't quite. You could check by factoring by grouping, but it doesn't actually factor out. Initially, it's really close, but there's one sign that's different. It doesn't factor out. We have no negative exponents. And so although it was ugly, we are done with that problem. All right, number 8. I have a little missing variable here for that base. We want to use the quotient rule to find y prime for this expression. And then we want to try to simplify the expression first and then find y prime, which by the way is going to be way easier. Yeah, that's such a better strategy by far. Okay, but what I'm going to do is I'll start with the directions. I'll use the quotient rule first. The purpose of this example is just to show you that you have choice in the order in which you do things. And that if you can simplify an expression, first do it. All right, but according to the quotient rule, it would be the denominator. A is just a constant, by the way. Sorry that wasn't stated. Times the derivative of the numerator. I'm going to use the power rule here. This is a constant. The derivative of a constant is 0. Minus the numerator times the derivative of the denominator. All over the denominator squared. Well, I can simplify this. I'm going to multiply out the terms on the numerator to see what I get. And then I'll check to see if I have any like terms. Maybe I can combine some stuff and make this a little bit simpler. Remember, we are not going to want to expand out or distribute out that denominator. We like that one because it's factored. Let's see what we got here. Do we have anything that will cancel? We have some terms that will combine, but nothing that will cancel. All right, so if I combine some like terms, I end up with x squared minus 2ax plus a squared. And I'm going to factor this. Well, this actually factors quite nicely to x minus a times x minus a. And you might notice we have this same expression on the numerator and denominator, so when you multiply something by itself, it simplifies to 1. We should notice that x cannot equal a because we'd get a domain restriction. Wow, that's kind of weird. Let's see if we can figure out why that's happening. Okay, I'm going to simplify this expression first before I try to actually take the derivative, and I'll simplify it by factoring the numerator and the denominator. Well, the denominator can't factor, but the numerator would be x minus a times itself and divided by x minus a, which if I reduce out a factor of x minus a, I would get that y is just equal to x minus a. Keep in mind that a is a constant. Y prime then, if I use the power rule, is just 1. And again, x is not allowed to equal a because there was a domain restriction for that. You might wonder, like, how much do you need to worry about domain restrictions? I mean, we're not going to mark you down for them, but it is just kind of a good practice for you to notice.